So we've been around since 2016. Our first product came out in 2019, which was called the CS1, based on the Wafer-Scale Engine, which our headline we keep talking about, the biggest chip in the world. But what made us think that the world needed yet another AI chip startup? And I'm sure you've all seen versions of this chart, but it really makes the point. Just in 2019, the biggest networks were about 100 million parameters. And we thought that was pretty big at the time. But in just 2 years, we've gone from 100 million to, just 2 years, we went from 100 million to nearly 200 billion. So that's 1,800, a factor of 1,800 in just 2 years. And that's not just compute requirements, that's memory requirements as well. And now we've got models that are much bigger than that, and it's not slowing down. The growth, if you plot this stuff, the growth of the largest networks is exponential, 12 times quicker than Moore's law. That's an absolutely terrifying growth. And there's no end in sight. We know, as someone mentioned earlier, that the bigger these things are, the richer they can be, the more insight they can show, the more accurate they can be, the better they perform on downstream tasks. So that's easy, right? We know how to scale out. We just add more nodes to things. The problem is that it doesn't work all that well as you get bigger and bigger and bigger. This is some data, just plotting some MLPerf results for a GPU. It doesn't matter which GPU. And you see that as you go from just a few systems to a few hundreds of systems, you get this tremendous little gap between the perfect scaling and the real scaling. This is inevitable, right? There's only so much you can do when you've got to deal with interconnect, memory bottlenecks across hundreds or even thousands of devices. So we looked at this, our founders looked at this and said, well, if we're gonna start from scratch, what do we want to do? We want to throw away all those bottlenecks, eliminate the memory hierarchy, down with the memory hierarchy as well as the patriarchy. Now, what we've come to realize is it's not just AI. The similar problems exist across HPC. Again, another cliche chart on the right here, showing the fact that the growth of memory bandwidth and network bandwidth is not keeping up with improvements in processors. And again, so there's this falling behind. And when you think about distributed computing, anytime you have to move any data between nodes, you're stuck with the latency limit of the fabric. And the fastest fabrics today give you latencies around 2 nanoseconds. So if you're talking about iterations, which is of course what deep learning and most of HPC codes are about, that gives you a limit of about 500,000 iterations a second. If you can keep it on chip, suddenly you're talking about nanosecond latencies and you're up in the billion region. So the prize is, there's a pretty big prize there. So we've got similar demands across workloads in AI at the mathematical level between AI, HPC, and converged HPC and AI systems, which are popping up everywhere. They all need massive amounts of sparse linear algebra compute. And if I had another half hour, we'd talk about sparsity for half an hour, but we won't. We need massive amounts of communication bandwidth and massive amounts of memory. The upshot, a new kind of processor. So that's what we did. We built this, the Wafer-Scale Engine. And
yeah, that was the first thing I was going to ask.
It's oh, sorry, I wasn't supposed to walk in front of the camera.
It's a myth.
The numbers are, of course, impressive. Hello, can we advance the slide, please? The numbers, of course, are impressive. It's got 850,000 cores. It's got 2.5 trillion transistors. It has holes through it. No one built a chip with holes through it. It uses an entire silicon wafer. It is a crazy piece of silicon. And we had to work with TSMC to find a new way to make chips this big, because it's way beyond the reticle limit. For those of you who know how chips are made, you know, you're stuck with a small chip, which comes to my next slide. These numbers are impressive, but they're more impressive in context. Now, I'm not bashing the A100. It's a very impressive work within the limits of a single reticle. So that postage stamp size chip. But by going bigger, we not only get 100 times more cores, we get to have 1,000 times more SRAM. Because top of the memory hierarchy is the best place to be. And because we can now move data with single cycle latencies, we've got 13,000 times more memory bandwidth and 46,000 times more fabric bandwidth across this thing. These are massive numbers. But you can't just take that thing, put a heatsink on it, and slap it on a PCIe card. You have to build a system. And that's what we built. So this is the Cerebras CS2 system. This shows a number of them installed in our colo just down the road. It goes easily into standard racks. It's a network attached accelerator with its own IP address. It's not dependent on the host server. And it's really quick to install. You roll it in, you connect the water, and you're up and running in about a half a day. While we're at it, let's just take one of these apart a little bit. So if you inside it, behind the doors, everything on the front is field swappable. Those are the things with fans that might break. And then at the back of it, we have the guts of it, the engine block, as we call it. And it's called the engine block because, at least to my eyes, it looks a bit like a 3-cylinder gas engine. And this whole thing is dedicated to keeping that wafer safe. All the stuff here is power delivery. The data comes in through the bottom and the top, and then this is the heat exchanger, which keeps the thing at a stable temperature. Now, if we break that apart again, and by the way, if you go to our website, there's a nice animated version of this you can play with under the system page. You can see these are the power supplies that introduce power to the wafer from the front. We can't, the power density is so high, you can't bring power in through the sides because it would melt. And also it would be, the wires would be so big, it just wouldn't work. So we bring them in through the top. And if you do the math on this, we're talking about 20,000 amps at about 0.8 volts. So it's a very impressive, there are some very impressive numbers in here. Then the wafer itself is in here, sandwiched between the power delivery system and a cold plate, which pulls heat out of the back of it. Data comes in from the edges of the wafer with these two I/O boards, which also contain optical engines because you bring the data to the system in the optical domain and then convert it, of course, to electricity for the actual wafer. So that's the guts.
So maybe you mentioned this already, Rebecca, but how do you get data in and out of the system so quickly? I mean, if you got thousands and thousands of cores that are consuming the data, you're powering it, intensely. I understand all that, but getting massive amounts of data into this solution and out of it's got to be a problem.
Indeed, it would be. You can just see. Oh, I'm sorry, I've gone back up. No, don't worry about it. On the front of the system, there are from these boards here. We've got this is cool. This is cool. We've got these are the optical Ethernet ports, and there's 12 of them at 100 gigabits each. So
1,200 gig each optical network inputs, outputs.
1.2 terabits per second.
1.2 terabits.
You can see the thing is installed in a rack with some support nodes. So depending on the workload, there's a number of ordinary pizza box servers there that deal with data marshalling to it.
And that lower cabinet is effectively the Cerebras system in and of itself. That doesn't include the storage or anything of that nature.
No. The support nodes act as a cache effectively for it.
Right, it's elsewhere.
But the 40 gigabytes of SRAM is enough. It's sufficient to hold any network up to some hundreds of billions of parameters. Beyond that, we have to switch into a different execution mode, which I haven't got time to go into today. But the thing is effectively scalable with linear scaling across systems to trillions of parameters. We know it's going to work to at least 100 trillion parameters, which is what we call brain scale. And that's fairly terrifying.
Okay, so those connections would be Ethernet type connections?
Yes.
Okay.
Yeah. But from the outside world sees the support nodes. Okay, now we've all seen wonderful hardware projects go nowhere because the software stack wasn't there. This is really, really easy. Users take their standard TensorFlow or PyTorch code. They flip a couple of library calls, so it's calling our libraries rather than standard libraries, and they're off and running. The compiler takes care of breaking that down into an intermediate representation, matching it to the pre-written kernels for different layers and functions, placing them on the wafer, and they're physically laid out on the wafer. So this part of the wafer is layer 1, this part of the wafer is layer 2, this part of the wafer is layer 3, and then creating the executable for it. We also have an SDK for HPC users, which allows them to program directly for the cores. Okay, just quickly, each one of those 850,000 cores, we actually call processing elements because the word core is a little bit ambiguous. And each one contains a general purpose processor designed for sparse linear algebra, local memory, and a programmable fabric router which is a 5 radix 5, so it connects to they connect to the 2D mesh and to the local processor. And this means that we can move data in a single clock cycle from processor to processor or from memory to the processor. And we call it data flow because there's no central coordinator keeping all of this going. When data arrives, the data packet tells the pre what to do. Do a calculation, pass the data on, whatever it is. So that's how the data flow works. Okay, let's talk about a couple of real-world examples. Using natural language processing is pretty common now for doing pharma work. But we know, or our friends at GSK realized that genomes alone aren't enough to do accurate drug discovery because the genome we used to think of as a blueprint, but you need to actually understand the epigenome, all the stuff around the genome to know exactly how things are actually going to be expressed in real organisms. The problem is that means much more complicated natural language processing models and much larger data sets, which today leads people to intractable training times, which is where we came in and gave them 10x faster than a 16 GPU cluster. Now, if you recall that scaling chart from earlier, if you wanted to match the training time, you need a lot more than 160 GPUs to do that. Now, we know they like this because they wrote a paper. And it's really nice to see our name in the title of the paper they wrote, Epigenomic Language Models Powered by Cerebras. And while the numbers are impressive, also it's the ease of use that they highlighted. One of our other pharma customers mentioned that the high cost of experimentation, by which they mean time and people, as well as electricity and systems, means that developers are effectively punished for attempting to make their models better. This lets people experiment and cycle and keep going quickly through different ways of attempting to do a task until they find something that works.
Rebecca, I'm just trying to understand if you can go back to the prior slide, which had the comparison. The 16 GPU node solution is not 16 GPUs, but the 16 GPU, it's almost like, multiple GPUs per node, right? It's a 16 node.
Let's be clear, this is one box with 16 GPUs in it.
Oh, okay.
So this is
versus Cerebras, which has, almost 1000x the performance, CPU compute and stuff like that. Is that how I would look at this? Because is it a fair comparison? I guess my question.
It's a fair comparison in the sense that you're comparing one box with another box.
Yeah, but your box is a lot bigger than a 16 GPU box, I think.
Two of them, yeah.
Yeah, and number one, and number two, your wafer scale level is a lot more compute per square inch, let's call it.
Absolutely.
It's unfair.
Oh, well, thank you.
Yeah, okay.
Yes, absolutely.
All right. Yeah. Okay. I'm just trying to understand how fair this
Well, it's fair because this is the way the GPU laden box is the way this stuff is done. And our assertion is that for this big stuff, this high-end work, there's a better way. You don't have to put up with sublinear scaling for these things. Let me give you an example from HPC. Our friends at TotalEnergies Research and Development USA, the energy business is full of big decisions. Where are we going to drill? Is this site going to work for carbon sequestration? Where do we put a wind farm? And these decisions have consequences. They have to be made really quickly because it's a very cutthroat business, and they're committing huge resources, and they won't know if they've drilled in the right place until they've done the drill and found out if the simulation was correct. So they're very interested in getting better HPC. And they're always looking for improvements, any fairly marginal ones. So imagine how happy they were at getting 2 orders of magnitude over a single GPU in this case, which is their benchmark. because all this stuff's proprietary. What they do with us is run benchmarks, and then they take it inside and do their own thing. Now, they also wrote a paper. And as well as the impressive performance gain, because 228 GPUs is a lot, the thing they liked was the fact, and these are magic words in the HPC space, is the algorithm used to be memory bound, and now it's compute bound. And also near perfect weak scaling. So these are things that make them very, very happy, and they're wandering all over the world telling people how happy they are. And now an HPC plus AI example. We have two systems at Argonne National Laboratory. In fact, they just upgraded to the new one, which is always a good sign. And they're doing a study with a whole load of other people to understand how the COVID replication mechanism works. So this is an intricate biological mechanism, millions of atoms moving in 3 dimensions. And this thing is big science. They're using researchers from 12 labs, and they're actually running this thing across 4 supercomputers across the world. Our bit is a computational steering part, because of course these simulations take a long time, they're very expensive, and you want to know if they've gone wrong. So they use a computational variational autoencoder in the loop to determine, which they're continuously training, to figure out if the experiment's going in the right direction. And they were very happy with us because the system was roughly equivalent to 100 GPUs. And they also liked, they wrote 2 papers, and they've done this twice now. One using their own internal system, and one using this really big system. And it's the thing I like here is that by including us in the loop to do this steering, they're able to get a 50 times improvement in their overall time to solution for this whole massive experiment. Okay, another pure HPC one. The National Energy Technology Laboratory is responsible for the nation's energy security, and they're using our system to do a CFD application, which uses a stencil algorithm, as you'd expect. And this is one of those things that's normally limited on each core by memory speed as you cycle through the elements, and the problem size by the fabric speed as you go between nodes.
So you have any idea of how much storage these sorts of systems had, and how much DDN, exascale, AIX, whatever the 400 nodes were in these sorts of configurations? I mean, you're showing impressive compute speed ups, obviously, but the storage also has a place to play in this space, and I'm just trying to understand where that plays. Maybe Kurt, maybe you. I think
it's a Kurt question.
Yeah,
because we're lucky enough that the data does get to us.
More basic question first. What is CFD?
Oh, sorry, computational fluid dynamics.
Yeah.
Okay.
So it's how you model things like wind
Airflow,
fields,
water flow,
and what they want to do is make it real time.
I think there's a couple of good points to that question, right? That you asked about where is the storage component of this, right? And the one thing I think that goes back to James's one of his first slides around the ML factory, right? And the fact that we now have a lot of different machines that are doing work on pieces of the data, or they have, specific parts of the workflow that they're working on, right? Some of it is CPU clusters, some of it is GPUs, and some are Cerebras systems, and they've got other things that they want to be. So it is the glue point.
Second. I mean, are you able to provide that sort of data?
Yeah, I mean, you go back to William's slide, right? And we have multiple deployments that are in the multi-terabyte per second range of storage.
But each of those nodes was like a 90 gig per second sequential read. So I mean, to do a terabyte per second would require 10 of those kinds of things. Is that what we're talking about?
That's exactly what we're talking about. Yeah. And so part of the reference architectures that we do with our partners is to ensure that the ratio is correct, right? So if you've got 2 Cerebras systems, you need X number of AI 400 X2s in your rack to be able to build that. And as you scale those out, right, you buy 5 more because you right, or developing more intensive models, you build out with those same. And so I noticed, right, there were two great observations from folks in the room. All right, one is, or actually on the line as well, right, that this is bonkers stuff in a good way, right? And I think that gets back to what's unique about DDN, right? We've been in this bonkers space for a long time, dealing with these issues, but we've simplified it down, right? Cerebras can do all these things, a single system, DDN, 90 gigabytes out of a single system with scalable building blocks that as you put these things together, right, they just scale linearly. And so we've simplified a lot of the bonkers work that's out there, right? And things that used to take, somebody with a PhD to manage these systems, it's now standard IT management.
And just to chime in, I think the other really important point, and I think we have to wrap up and pass it back to James to finish, but the most important part as well is over the last 4 years, there's a big body of work that's been built. So the reference architectures, for example, and there's a lot of FUD, everybody's got a reference architecture. What's different with us is ours has been validated. It's been validated for 3-4 years. And so we've tested it at a massive scale. Customers are running all sorts of workloads, and they're publishing validation data. So similar to the papers that Cerebras is showing here, validating how their solution actually makes a big difference. It's the same for us across the entire ecosystem, and no other storage provider has that level of depth.